Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Shafiq Aiman bin Suhirman. My metric ID is MA20124. I am from Group 6. I will start the presentation of our experiment for lab 3. Lab 3 is the friction flow in pipes. So I will start the presentation with the introduction. Due to the consequences of the continuity equation, the input of fluid entering the pipe will be equal to the output of fluid exiting the pipe. Typically, components vary the cross-sectional area of the pipe system to change the flow direction, obstruct movement, and change the flow rate. Bends, elbows, and these devices that change the direction of flow are just a few of the parts that make up pipe system. Valve adjustments are made to flow rates. To slow down or speed up fluid motion, expansion and contraction are used. They can happen suddenly and gradually. Exit from pipe system into reservoir or an extraction into pipe system from reservoirs are like what's regarded as component. Many different parts are used in this experiment, including the abrupt 45-degree angle pipe, bend pipe, straight pipe, and elbow pipe, which cause the flow to change direction quickly. If the flow direction changes too suddenly, distinct flow zone where eddies form happen, increasing component loads. The various environment and circumstances in actual situation are taken into consideration while managing head loss in pipes. A fluid flow lamina or turbulent nest can be determined using Reynolds number. In general, when fluid viscosity rises, head loss also rise, especially near fittings, potentially slowing flow rate. We go to the problem statement. We should take into account two laws when calculating the fluid friction in pipes. The first is that when a component, valve, bend, or other disruption happens inside the pipe, there are big losses or major losses. And the second is that there are minor losses as well. Consideration include the flow velocity, pipe length, pipe diameter, the friction factor based on pipe roughness, and whether the flow is laminar or turbulent. When there is resistance created by fluid flowing via pipelines, pumps, and fittings, friction loss take place. Depending on the type of pipe, friction loss varies. Friction loss varies. Additionally, as the frictional head is gone, the fluid internal energy rise. If a piping system is effective, the user should experience fewer energy expenditures, less maintenance, and increased productivity. In this experiment, we investigated the mechanics of fluid friction, applied phenomena, and applied rudimentary knowledge of significant losses in pipes. So for the objective of the experiment is to describe the principle underlying the fluid friction phenomenon in pipes. The second one is to recognize and use fundamental information about large losses in straight pipes. And the last one is to recognize and use fundamental concept related to tiny losses in straight pipes. So we go to the theory of fluid friction in pipe. Both interval viscous shear force in the fluid and turbulence that develop along the interior pipe will prevent a gas or liquid from flowing through a pipe. As energy is required to resist the viscous and frictional force produced by the pipe walls on the flowing fluid, there will be a pressure loss in the fluid. Energy is lost as fluid passes through fitting like valve, elbows, construction, and expansion because of frictional forces. In pipe flows, the pressure of loads is referred to as head loads, while tiny frictional loads are brought or by fittings like mesh, coupling, valve, or transition between hose and pipes. They are largely created in straight pipes. Major loads are those produced by friction, whereas small loads are those brought on by fitting. The viscosity of the fluid, the radius of the exterior and internal pipe, the roughness of the internal pipe surface, the difference in elevation between the pipe ends, the kind of material, and the length of the pipe along which the fluid runs are all factors that affect pipe losses. Next, we go to the friction loss in pipe. The causes of friction loss known as major loss in straight segment of pipe include the effect of viscosity, the movement of fluid molecules against each other or against the wall of the pipe. The amount of the friction loss in a pipe will be strongly impacted by the kind of flow, such as turbulent or laminar. Laminar flow is the movement of fluid particles in layers or laminas along parallel streamlined or smooth, well-defined channels, effortlessly flowing over one another. The motion is highly organized, and the laminar flow Reynolds number is less than 2,300. For the transitional flow, when laminar flow changes to the turbulent flow, transitional flow occurs. This flow has a Reynolds number of between 200, 300, 2,300 to 4,000. The last one is the turbulent flow. When fluid layers are blending and moving quickly, there is turbulent flow. At each point, the fluid is moving in a different way, both in size and direction. It should be observed that when the flow is entirely turbulent, the friction factor will be at its highest, which is like more than 4,000. When describing this roughness as the proportion of the pipe diameter to the roughness height, the term relative roughness is helpful. There are three subdomains inside the turbulent flow domain. The first one is the friction loss in insensitive to roughness in smooth pipes. Next one is the rough pipe. Relative roughness predominates friction loss, while Reynolds number is unaffected. The last one is the transition domain. Roughness and Reynolds number influence friction loss. That's all for me.
Assalamualaikum warahmatullahi wabarakatuh. My name is Syed Muhammad Faisal bin Syed Mahaza. My ID number is MA20098, and now I'm here to present about the experiment procedure. For this slide, it shows equipment and material that we use for the experiment. We use fluid friction apparatus, hydraulic bench, and pipe elbows, as shown in the figure above. Now, I'm going to explain about the experiment procedure. For the first procedure, pipe flow friction factor. Number 1, the appropriate section of the fluid flow apparatus is used as in section A. Number 2, the fluid friction apparatus is set up as mentioned in the experimental setup earlier. 3, the dual pressure gauge for appropriate water column height is set up. 4, with the pump running, 7 different variations of fluid flows are altered to provide 7 measurements of volumetric flow and heat loss. Number 5, the required values are recorded. For the second procedure, pipe elbow loss coefficient and equivalent length. Number 1, for this experiment, an appropriate section of the fluid flow apparatus was used, which is section B. 2, the fluid friction apparatus as mentioned in the experimental setup earlier was set up. 3, the dual pressure gauge for appropriate water column height was set up. 4, the pump to set the volumetric flow is at the maximum value that was set up. 5, the dual pressure gauge at the first set of elbows, which is the pipe elbows, was attached. Number 6, the heat loss is noted across the pipe elbows. And for the last step, step 5 and step 6 were repeated using 90-degree pipe bend and the 45-degree pipe angle.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Wan Muhammad Nasrul bin Wan Muhammad Najib. My matrix ID is MA20215 and I am from Terengganu. So I will continue the presentation for our lab 3 fluid frictions for the result and discussions. Okay, the first one is for the parameter and the formula. So the formula we use is such as the pipe friction coefficient, flow speed, head loss, and the Reynolds number. And the parameter that we use is such as the major losses in straight pipes, which is the length of the pipe, the PVC pipe interval diameter, PVC pipe thickness, density, and also the dynamic viscosity. For the next one is the result. First we go for the turbulent flow. As we can see that this is the data that we calculate, and from the data from at the volumetric flow from the experiment, and also we measure the head loss from the experiment in order to calculate the flow speed, the Reynolds number, pipe friction coefficient, and calculated losses coefficient. And this is the graph that we gain from our data, which is the pipe friction vs volumetric flow and the head loss vs volumetric flow. So the pipe friction, the maximum is 0.0321 and the minimum is 0.0283, while for the head loss, the maximum is 0.0359 and the minimum is 0.0149. And we can conclude that when the volume flow rate increase, the pipe friction will decrease, while the head loss will increase. Then we go for the straight and elbow pipe. So the first table is related about the straight pipe, and the second one is the elbow pipe. Next, we also calculate for the bend pipe for 90-degree and also the 45-degree. So the first table is about the 90-degree bend pipe, while the second one is the 45-degree bend pipe. And then from that four elements, we have construct this four graphs of the pipe frictions. So as you can see, all of the graph is have we can conclude that when the volumetric flow rate increase, the pipe friction coefficient will decrease. For the head losses, as you can see, there is a various strength for different in our different graph. So for the first one, we go for the straight pipe of losses. We can see that the strength is going to be decreased when the volumetric increase. Next, for the elbow pipe, you can see that the graph is increased and then it is slightly decreased. And for the 90-degree bend pipe and the 45-degree bend pipe, we can conclude that when the volumetric flow rate increase, the losses coefficient will increase. Next, we go for the discussions. For first one is the pipe flow friction factor. The first question is what the conclusion can be made from the head loss and the flow speed. So we have to increase the flow rate, and the head loss will we increase the flow rate, the head loss will also increase. And the water traveling in the pipe or channel has the head loss due to the turbulence caused by the water's velocity and the roughness of the pipe. The second question is what would happen to head loss if the length of the pipe is increased? And the answer is the head loss will increase since the head loss is directly proportional to the pipe length. The third one is the what would happen to head loss if the diameter of the pipe increase. So the head loss will decrease since it is inversely related to pipe diameter. And then the head pressure from the pump will significantly increase if a smaller diameter is used. So it is recommended to utilize pipes with the largest possible diameters. Then we go for the pipe elbow loss coefficient and equivalent length. For the first question, what is the relationship between the flow speed and head loss? The head loss in the pipe will grow as the fluid's volume flow rate increase, and the head loss is directly related to fluid velocity. The second one, what is the connection between the elbow and bends in terms of its turning radius, head loss, and loss coefficients? So the head loss coefficient assesses in the inlet's capability to smoothly transfer flow, and the amount of energy lost as a result of pipe bending, it is known as the head loss. And then the velocity of the flow change as a curve is introduced to the pipeline. For the last questions, what is the conclusion can be made considering elbow and bends in the terms of its turning radius and equivalent length? So for our conclusion, we can conclude that an elbow's radius is smaller than that of a bend. And from 1 to 2 times the pipe diameter is the range of elbow's radius of curvature, and more than twice as large as the diameter of bend radius of curvature. So I think that's all for me. I will pass it to my friends. Thank you.
And for my last part is for the conclusion. For the conclusion, the Darcy-Weisbach equation successfully identify all of the experiment parameter strengths and relationship. The pressure drop parameters were also thoroughly experimented with and analysis in order to gain a better understanding of how pressure drop occurs and the critical elements that influence it. The experiment demonstrate that different types of minor losses have different values of head losses and that volumetric flow is related to head loss. One of the factors that has the greatest influence on pressure drop is viscous fluid, also known as Newtonian fluid, which is a fluid that does not flow smoothly and can result in laminar or turbulent flows. That's all from our presentation. Thank you.